Next is asynchronous up-down counter. So, what do you mean by an up-down counter? You know what an up counter is? Up counter will count up. That is, if it's a 3-bit up counter, then it will count from 000 to 111. If it's a 3-bit down counter, it will count from 111 to 000. So what is an up-down counter? 3-bit up-down counter, what will it do? In that circuit, we can decide as to whether it should count up or whether it should count down. So you have a circuit which can count up as well as down. So how will we decide whether it's counting up or whether it's counting down? You have a mode control. Okay, mode control means that mode control, it's a control signal, 1 bit, which will decide as to whether it is going to count up or whether it's going to count down. So here we are going to consider 3-bit asynchronous up-down counter. So we know that in up counter as well as down counter, we are making use of T flip-flops, or if you are using JK flip-flop, you will connect it as T. So let this be T0, T1, T2. You will be keeping the LSB flip-flop here. Why? Because with every clock pulse, the bit that changes with every clock pulse is the LSB bit. So you are applying the clock directly to the LSB flip-flop, and we are making use of the complementing of the flip-flop logic. So you'll be connecting all the T flip-flop to 1. So these are the clocks. So what is our logic? If we are going to count up, then each flip-flop except the LSB flip-flop. For the LSB flip-flop, you are giving clock as clock directly. For these two flip-flops, in T1 is clocked by Q0 if it's up counter. So every previous output will clock the next flip-flop. So Q0 will clock Q1, Q0 will clock T1, and Q1 will clock the flip-flop T2. That is up counter. So if you are going to count up, then the Qn or Qn minus 1 will clock the Tn flip-flop. T1 is clocked by Q1 minus 1, Q0. T2 is clocked by Q1. Likewise. Okay. So if it's a down counter, then Tn is clocked by Qn minus 1 complement. Yes. So that is the logic. Up counter means this, down counter means this. So whether it is up counter or down counter, that is decided by a bit which we called as the mode control. I am notating it as M. M is a bit, single bit. M can be 0 or 1. So let's say that if M is equal to 0, then it will up count, and M equal to 1 means it will down count. Suppose So if m is equal to 0, then it should up count. M is equal to 1 means it should down count. So m equal to 0 means Qn minus 1 should be connected to Tn, to the clock of Tn, and m is equal to 1 means Qn minus 1 bar should be connected to the clock of Tn flip-flop. Okay, so how can we write this? A particular clock except this, except the LSB flip-flop, the other two clocks, since it's the 3-bit counter. If you have a larger number of bits, then all the flip-flops except this. So the clock of a particular flip-flop is clocked by whom? If m is equal to 0, then the corresponding q. Okay, I'm not writing it as Qn minus 1, etc. I'm just writing it as Q. It is, what I mean is the previous itself. Or you can, to be very specific, you can write m dash Qn minus 1. If m is equal to 0, Qn minus 1 will clock it. Or, if m is equal to 1, then Qn minus 1 bar will clock the flip-flop. So what is this? M bar Qn minus 1 plus m Qn minus 1 bar. What is this equivalent to? This is m XOR Qn minus 1. So a particular clock is m XOR the previous output. Yes. So if we implement this, so suppose this is my m, and this is a switch which I can move. You can keep it at 0 or 1. So if it is 0, then Q0 should clock. So what is my equation? Clock is equal to m XOR Qn minus 1. So what is the equation for this particular clock? It is m XOR Qn minus 1. Here what is it? It is again m XOR yes, and where will you take the outputs from? You will take the outputs from, the LEDs will be connected to Q0, Q1 and Q2. This is my Q0, Q1 and Q2. You will be reading it like this, Q2, Q1, Q0. This is my MSB. I'm just drawing it the reverse way, but reading, I'll be read like if it is 1, it will be counting like 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, likewise. You don't read it like from left to right, you read it from right to left. Yes. So that is asynchronous up-down counter. So, how do you write the truth table for asynchronous up-down counter? You can just combine both the synchronous and asynchronous truth tables. You'll be keeping an extra bit m. So, it will be m, q2, q1, q0. So, clock 0 means if m is 0, it is 0. Then m is 0, for all these m is 0. Then if my m is equal to 1, this is 0, 1, 2, 3, 4, 5, 6, 7. This much is up count. Okay. Now if my M is 1, again clock is 0, because up count, it's not the continuation of up counter. It is either up count or down count. Okay. So when you start with M equal to 1, then again this is the initial condition. So it should start with 1, 1, 1, then 1, 2, 3, etc. So it should count down 6, 5, 4, etc. So for all those, M is equal to 1. So that is how your truth table will look like. Now there is something called the timing diagram. So timing diagram shows us how the output changes. Okay. So for that you need to draw the clock. All should be equally spaced. So it is 1, 2, 3, 4, 5, 6, 7, 8, etc. So this is my clock. Now each clock I am taking it as negative edge triggered. So for that I'll notate it using a arrow. Negative edge triggered flip-flop. So I'll notate it with an arrow at the negative edge. Then I'll draw a line which shows that the flip-flop is triggered at that particular edge. Okay, a change happens at Qn plus 1 at this particular edge of the clock. Then I'll write the outputs. Okay, so in the case of 3-bit, I'm going to draw the timing diagram of 3-bit up counter. So if it is Q2, Q1, Q0. So I know that. So this is the first clock. In this first clock, the flip-flop is triggered only during the negative edge of the clock. Before that, to its left, that is the initial condition. Because the first clock has reached, that happens only at these lines. Before that, it's the initial condition. So what is the initial condition for an up counter? It is 0, 0, 0. Q2, Q1, Q0. When the first clock comes, what do I get? I get 0, 0, 1. Second clock, after the second clock, when the flip-flop is triggered at the second clock, what do I get? This is clock 1. Clock 1, clock 2, clock 3. So, clock, after clock 1, it is 1. After clock 2, it is 0, 1, 0. After clock 3, it is 0, 1, 1. Clock 4, it is 1, 0, 0. Clock 5, 6, and 7. After that, if I apply another clock, what will happen? It will go to 0 again. So this is my actual truth table. Now using this, I'll just draw. So how do I draw? Zeros, I'll keep it at low. Low. 1, I'll keep it at high. So it is 1, 1, so I'm keeping it at a higher voltage. Then it goes to low. So zeros, I'll keep it at low. 1, I'll keep it at high. Again low. Here again 1 is happening. Then low. Here low. High. Low. High. Low. High. Okay, so this is the timing diagram of 3-bit up counter. Which 3-bit asynchronous up counter. Asynchronous or synchronous, it will be the same only, but since we studied only the asynchronous, this is that. Okay, so if you write these zeros and ones, it's easier for you to draw. You won't go wrong, and also it's easy for the evaluator to evaluate that it's correct. Otherwise they'll have to think whether this is correct or not. They'll have to double check. If you write like this, okay, what is written is correct, so what you have drawn is also correct. So it's always good to, when you are drawing a timing diagram, write first then draw. So it's easier for both the cases. You won't go wrong, and for the evaluator also it's right. So if you have to draw the timing diagram for a 3-bit down counter, similarly you can, again it's the negative edge. So initial state is before the first clock, so that is 7. First clock pulse 6, second clock pulse 5, 4, 3, 2, 1, 0. If you give another clock pulse, it will return to the initial state. That is a down counter. So that will be 7, 1, 0, here 1, ones, will be 0, 1, zeros and a 1, 1, 0, 1, 0, okay. So this is timing diagram of a 3-bit asynchronous down counter. Okay. So if you need to draw the up down counter, you'll have to draw another line. for M also. So if M is 0, then this will go on. If M is equal to 1, then it will count on. But this won't fit inside this. Normally you'll be asked for up counter or down counter only. So if you are asked to explain a 3-bit asynchronous up counter, you can first write the truth table. You can draw the circuit, explain how it is drawn, what is the logic, then you can draw the timing diagram. Similarly for the other circuits also.